Hey, good afternoon, guys. So, the premise of this talk is essentially RAM prices are not getting cheaper, right? They are going through the roof, and users want faster applications, you need more memory, and yet the data that you're storing is keeping growing, right? So the premise of this talk, and for the next half an hour, 45 minutes, I'm mostly talking about how do you store more data in Redis in the same amount of memory, and either to increase the data that you're storing or to reduce your cost. So that's the entire premise of this talk. My name is Sripathi. I'm the CTO at HashedIn Technologies. Also, we launched RDB Tools, a tool that helps you in memory optimization. I'm one of the top answerers on Stack Overflow. You'll find me on GitHub. I'm the author of the tool Redis RDB Tools along with Oren out there. That's a little about me. Those are my handles. So the talk is about in 4 or 5 parts, right? The first part is essentially how do you optimize key value pairs, right? You've got a key, you've got a value. The value could be Java serialized object, could be a message pack, could be a JSON. So how do you optimize key value pairs that you've stored in Redis, right? So let's look at a very common thing, right? You've got an object. Let's look at, imagine these as Java classes, right? You've got a user object, and user has one-to-many articles, right? This would typically be from a database, a SQL database, and you're trying to cache that in Redis, right? The question is, what happens when you've got the same user having multiple articles, and multiple users have the same article? So now you try to cache this in Redis. The same article is being stored in Redis multiple times, right? Because if you blindly cache an object that you've read from the database and not made the effort to normalize your object, what happens is you're storing a lot of duplicate data. In this case, there may be a very popular article, and that article is being, multiple users are sort of favoriting that article. So what happens is that article object in Redis is being duplicated. So what you should end up doing is normalize your object. It's a kind of similar principle to what we do in relational databases. You split your object into various things. Any relationships or pointers between objects, try to use it into a set. So you basically have a user's object, you have an article's object, and the relationship between them, store that in a set, right? Like users :ID :favorite articles. You'd be surprised. This is a very, very, it may sound like, this is so simple. Why would why does I need to talk about it? But a lot of times we use frameworks. If you're coming from Java, Spring Framework, Django, whatever, and you just put an annotation on an object and say cache this. But behind the scenes, it's essentially storing a serialized version of your data. And if you don't pay attention to this, you're just storing GBs and GBs of data for no reason, right? So the tip number 1 is normalize your data, right? Make sure that you're not storing redundant information in Redis. That will go a long way in reducing memory. The next thing, right? How many of you guys use Java, and do you store Java serialized objects? Anyone in the audience, right? So Java serialized objects it's not a good it's a great serialization algorithm in the sense that it can serialize any object, right? But there's a cost to that. A Java serialized object stores the entire class name, stores the entire field name, the method name, the entire class hierarchy. If you've got 3 levels of inheritance, it will store all the superclasses in the serialized object. All of that takes a lot of memory, right? So a Java serialized representation of your object is not optimum from a Redis perspective. So 2 problems with that. You're wasting a lot of memory, and then every time you're going to Redis to fetch your object, there's a network cost to it. So what do you do instead? There are better serialization algorithms out there, right? So Cryo, that's a great serialization algorithm. If you don't want to change any of your code, it's almost drop-in replacement for Java serialization. So you can use that. You get a good savings on the serialized version of your object, and it's a great way to reduce memory. But you can do much better than that. If you are willing to modify your code or schema, there are better serialization algorithms, right? So there is protocol buffers. The protocol buffer is by Google. Flat buffers is also by Google. There is message pack. So these are even better serialization algorithms. They don't need to store the class name, the field name, and therefore the serialized object that you save in Redis is far more optimized. This alone can easily reduce your object size by 50%, sometimes even higher than that. So the summary is, you don't want to change code. It's a very complex nested object. Try to use cryo. If it's a flat object, not too much hierarchy in it, try to use message pack, protocol buffer, flat buffer, whatever. There are several serialization algorithms. Anything that is binary and optimized is good for Redis, right? The third is compressed data, right? And especially if you're using key value pairs and you're using something like JSON. JSON is a textual format. It's not optimized to be stored in memory, right? So if you're using JSON or a textual representation, compress your data, right? Now, the common question that we say when it comes with compression is, what is the latency that I'm introducing because of compressing, decompressing, right? So there are different algorithms, right? So this example, the Snappy algorithm by Google, right? It optimizes for decompression, which means that it trades off. The trade-off over there is you will get an average compression, but the decompression, whenever you try to decompress it, it is really fast. Now, in the case of Redis, you are using it as a cache, which means you want decompression to be very fast. You don't want to increase additional latency over there. So LZO, Google Snappy, these are algorithms which help in that trade-off where you're not using too much CPU in the decompression side. But if you are interested in more compression, there are other algorithms. They will be a little slower than Snappy in terms of decompression. But that's a trade-off that you as an application, right? So the summary of it is, textual data, please compress. Latency, from a latency perspective, if you cannot tolerate latency, try out Google Snappy. It's great for that purpose. If you want more compression, reduce even more memory, try the other algorithms, right? A quick way to benchmark, this GitHub repository has done all the benchmark, all the comparisons across various data sets, across various algorithms, and it's a very handy reckoner. Pick up the algorithm that makes sense for your programming language, for your use case. But compression is a very easy way to get another 50% reduction on your data size, right? Especially if you're using a textual representation, a textual format. So moving on. Another way, right, instead of compressing, is to use message pack. If you're not familiar with message pack is like JSON, but it is binary. And therefore, it is smaller, it is faster to access. It is even faster than JSON in terms of serialization, deserialization, right? Message pack is supported in 50 plus programming languages. Even Redis Lua scripts can interpret message pack. So which means that if you've got a big complex object that you stored in Redis, you can write a Lua script to access only portions of that object, right? You don't have to fetch the entire message pack object into memory. Message pack is great. It will reduce your size significantly. Just go to messagepack.com. It has a very interactive visualizing tool which shows you that given a JSON, what does it look like when you store it in message pack. So another great way to reduce memory, and especially because it is supported by Lua scripts, the other thing that you can do is only get portions of the object in back into your application. So the fifth recommendation, right, is combine small objects, right? So let's look at this data structure that we're trying to store, right? So you've got your keys, which is zip codes, and the values is a small JSON object with the city and state information, right? So let's say that you're trying to save this. Now what happens is each key in Redis has some overheads, right? And when you have separate keys for each zip code, the overheads are significant. So a quick way to win this is, try to store your data in this manner. So instead of storing it as key value pairs, introduce a hash, right? Now in the hash data structure, you kind of split it, you combine similar keys, and you say, well, I will take the last 3 digits and make it the field name. So when you're trying to do a lookup, right, let's say that you want to get the city and state for the zip code 90210. What you do is you break it up into one portion of the key, which is a hash, and then the next 3 characters will be the field within the hash, and then you get your object value, right? what this does is the cost of a top level object in Redis is now being shared by, it's being reduced, because in this strategy you can go up to 500, around 500 elements, right? 500 elements into your hash data structure. There's a great blog post by Instagram. It is a little dated, but the principle and the premise on how this optimization works is very well written by the Instagram engineers. They stored, hundreds of millions of keys in Redis using this technique, and it's a great strategy, right? The one thing that you should be aware of, if you compare this one, the version on the left, you can set an expire to individual keys. On the right, the version on the right of your screen, you cannot have an expiry on individual fields within your hash. So that is a limitation. But if you can bear with that limitation, then this is a great way to reduce your memory usage. You will it will be a significant win for you guys. Sorry, I just wanted to. The optimization works only if your hash, the resulting hash that you've created, is of a particular size, right? And the elements are smaller than a particular size. I'll talk a little bit about that a little later in the talk. But if the keys that you're storing, if the JSON that you're storing or the value that you're storing is very large, then this optimization does not work, right? So it's only for small objects and which you can combine into a hash. Going forward, if you are storing JSON in Redis, right? One recommendation that I would have is, instead of the JSON, try to move to a hash. Now, Redis internally, make sure that a hash is using a very optimum representation or optimum encoding. So it's not that the memory savings will be too high, but you do get the ability to update or fetch only certain fields. So, whenever you can, try to use a hash instead of a JSON, and especially if your JSON is flat, right? Doesn't have too many nesting hierarchy, then it's perfect to just use a hash structure instead. Right. So, just an interlude. A common, these recommendations require you to make some changes, right? But if you've wrapped your Redis library into an application-specific class, right, and then using that interface, then it becomes very easy for you to introduce these changes, right? You can transparently introduce a compression algorithm. You can transparently change the serializer, right? So my recommendation is, first try to have a central class that is, a common class that is accessing Redis. Wrap your Redis library, and then it becomes very easy to try out different algorithms, try out different serializations, compression or no compression, those kind of things. So whatever programming language you're using, take your Redis library, wrapper over it, make a wrapper over it, and use your wrapper. It will become very easy to plug and play various things later on. So that's the first set of tips for reducing memory when you're storing key value pairs, or basically you're using the string data structure, right? The next section is about optimizing hashes, right? So hash is you have a key, within that you've got a field, and then you've got a value, right? So how do you optimize hashes? So this is a little pseudocode, but Redis internally stores hashes in two different formats, right? The first format is called a zip list encoding. It's called a zip list, and the other is a hash table. The zip list encoding is very, very memory efficient, right? And the hash table, it's not memory efficient, but it can scale up to a large number of keys, right? Even to millions of keys. So the zip list encoding is great from a memory perspective, but does not scale up, right? Now Redis, by default it is 512, I believe. But there's a property in Redis, it's called hash max zip list entries, which you can tweak. So the way Redis decides which encoding to use, right, is what is the size of the hash? Is the size of the hash less than hash max zip list entries, right? That is the first condition. And the second condition is any field, field and the value, it must be smaller than hash max zip list value. If these two conditions meet, then Redis uses the zip list encoding, right? Now, Redis has some defaults for both of these values. I believe it is 64 and 250, 512, right? Whatever. But if you open up redis.conf, it is documented what those values are, the default values are. The point is, though, if you're trying to optimize hashes, the trick is find out your data set and find out what is the right value for your data set for these two settings, right? So this is the basic principle, right? Every time you try to, if you want to optimize hashes, the basic philosophy is try to convert your data or manipulate your data so that Redis internally uses the zip list encoding. How do we do that? So here is where you can use RDB tools. So it's an open source tool on GitHub. Just go to github.com, search for Redis RDB tools. It can analyze your data and it gives you a CSV output. Using that, you can find out what your optimum setting could be for your values, right? That's one. The second is you will then go and increase these values in your configuration and restart your Redis server. The next thing to do is monitor how much, does it increase your latency? Now you cannot go about and increase it to any arbitrary value, because then that will bring down the latency. It will increase the latency of your commands. So what you should be doing is increase the value to a level that it does not increase your CPU utilization and it does not increase the latency of your commands. A quick way to check that is using the info command stats. This will give you the latency. Search for all the hash commands and check if it has, by making this change, has your latency for your commands increased or has your CPU utilization increased, right? So the general idea is tweak these two settings, increase them so that your hashes start using the zip list encoding, and then check if your CPU utilization is increased. You can keep increasing it till the time the CPU utilization is not high. I would say don't go beyond 1,500, but that's good enough, right? Hash map with 1,500 entries is good. Right, does that make sense? I mean, if there's any other question I can, well, okay. So that is how do you optimize small hashes, right? By the way, this is documented on the redis.io website. If you go to memory optimization, this is one of the recommendations. Now continuing on this, right? Let's say that you've got a hash and it looks like this, right? Now name, age, role, fairly small fields, but there's an about me section which could be a paragraph of text, right? So there is one field in the hash because of which this if condition breaks, right? Look at this if condition, right? How many entries do we have? We've got 4 entries in the hash. But what is the length of the largest field? The about me section or the about me field will be pretty big, right? As a result of which Redis will not use the zip list encoding. Let me just go back, show you, right? So the about me is one field in your hash which is causing Redis to not use the zip list encoding, right? So what do you do? The trick is then, and if this makes sense for your application, right? The trick is then take that one field and move it out of your hash. So then the top hash, right, user's hash, will start using the optimum encoding, and the other one will be separated out, right? So in this way, the bulk of your data is using an optimized encoding, but the other one, which you may or may not access every time, is stored in a separate data structure, right? Again, going back to the same philosophy, try to manipulate your data structure so that you are using the zip list encoding, right? Another use case is when you've got a very large hash, right? We come back to the same example of a zip. So you've got one large hash called as zip codes. The key is the zip code and the field is your information about state and city. Now, what do you do about this, right? Again, try to break it down into smaller hashes, right? So if you could break this down into smaller hashes so that you've got one top level key called as zip codes :90, and then within that you've got multiple elements and each element has your city state information. Doing this, because you're breaking a larger hash into smaller hashes, each hash itself can now use the zip list encoding, and therefore overall you're saving memory. Oh, right? So again, the trick is you are breaking into a smaller hash so that it fits into the zip list encoding. After you do this, you can readjust or tweak your zip list and your settings for max entries or max value, right? Now, I just want to have a small interlude. The example that I chose is purposely simple. Sometimes it's not easy to split so that you get 500 elements into a smaller hash, right? What if your key is more complex and does not have numerical parts into it? You can still use this technique. Just use a CRC or a hash of your key and then convert it into integer. So I think Redis Labs blog have a blog post on this where they explain how you could do it, how you can generalize this pattern. Even if you don't have numeric parts, how can you generalize this same principle and split a larger hash into smaller hashes? There is a blog post on the Redis Labs thing called, you should search for sharding hash. Just shard a larger hash, you will get that article. So just getting back, right? We use the same technique in two different places. The first slide we spoke about, when we had thousands of small strings, we converted that into hundreds of smaller hashes. And then you've got one large hash with thousands of elements. We did the same thing to get hundreds of smaller hashes. The idea is the same whether you start from multiple strings and combine them to a hash, or you start with a larger hash and combine them to smaller hashes. The idea is the same. The basic principle is that a hash, when it uses a zip list encoding, saves a lot of memory. So readjust your data so that you get one of that. You get it into format like that. The last one, which is for the hash, right? If you've got many hashes which have the same fields, the field themselves consume memory, right? So so let's say you've got millions of users, right? Each user has a name, age, whatever, role, field, right? The name, the age, the field, all of these field names themselves occupy memory in Redis, right? You can do the math, it's fairly straightforward. So depending on your use case, if you've got a very repetitive structure, it may make sense for you to make shorter field names, either shorter field names, or you can even use position-based index, right? For example, you could say name is position 0, age is position 1. Two things on this. Usually the memory savings are not worth it unless you have thousands of similar objects, right? So so that's one thing. Please do the math before you try to implement this. That's the second thing. And the third thing I would say is don't change your application code. Again, introduce a wrapper around the Redis library. So your application code is still using the field names, still using the regular commands, but the layer that you've written on top of your library sort of does this massaging. So it's easy to swap in, turn off all that feature, right? So that's it on the second section, which is optimizing a hash data structure in Redis. Okay. The third section is how do you optimize set. Now, when we spoke about hashes, we said hash were implemented in two types of data structures, right? A hash table and a zip list. Something similar for set. A set is implemented in Redis using two types of data structures. One is again a hash table, but the second is what is called as an integer set or an int set, right? An integer set is just a sorted array, right? It's a sorted array of numbers, and Redis does a binary search on this sorted array whenever it wants to find an element or insert an element, right? So in order for you to force Redis to use a more efficient implementation, the first recommendation that I have is try to use integers in your set, which means that if you can store your primary key as an integer format, so instead of saying users colon 13232 users colon Sripathi, if you can say this is the ID of that user and then store that ID in your set, it's going to be very, very efficient, right? So whenever possible, try to store integers in your set. That's the summary of this recommendation. Now, it may not always be possible to do that, right? So what you can do is if your identifiers, if you've got the same identifier storing across multiple different sets, it may be feasible for you to store that once in a separate hash, store that mapping between a string to an integer in a separate hash, and then store the IDs in a set, right, in an integer set, right? This may or may not make sense because you're now trying to introduce two different data structures, one for mapping from a string to an ID, and then looking up the ID into the set. So it may or may not make sense for your use case, the indirection, and it may or may not reduce memory. It will reduce memory only if that same string is being stored multiple times across your sets, right? So try this out. There are use cases where it helps a lot. There are use cases where it may not help so much because of the indirection between two different keys. And then once you have used you've converted into integers and stored it as a set, this is the one setting that you have to configure, which is set-max-intset-entries, right? This what this setting says is, if your set is composed of integers, what is the maximum that it can allow? Beyond that value, it will switch to a regular hash table. The default value is 512. You can increase it. Again, my recommendation would be don't go beyond 1,500. But depending on your use case, you can go higher, lower, and always check the latency. Always check the CPU utilization. But if you can use integers in your set, you will get a lot more savings, right? I mean, it's significant. The savings that when you start using an integer set are significant. Okay. Fourth is probabilistic data structures, right? Now, the question to ask is, why are you using a set in the first place, right? Now, it happens to be that there are 2 or 3 use cases, right? One is you want to deduplicate, which means that you want to find out, did this element exist in the set in the first place, because a set does not allow duplicates, right? So that's one use case. And the other use case is when you're trying to count unique elements, right? How many unique elements am I seeing? Now, if you have got a set which is very, very, very large, and you don't care about the exact number of elements inside that, or you don't care whether if there is a chance of failure, it's okay, right? Then you can experiment these probabilistic data structures. The hyperlog, it's an inbuilt command in Redis, and it lets you count the number of unique objects. So for example, you want to count how many different unique IP addresses made API requests to my web server in a given time period, right? Hyperlog is great for that, right? You could have stored each IP address into a set, and then that could have done a cardinality of that set. But instead, if you just put it into an hyperlog, it will give you a count. There is some math behind it, so the error is bounded, and Redis makes some optimization so that for lower values. So the net is, if you're counting unique items, try a hyperlog instead, because you don't want all the elements in your set, right? Another thing is if you want to find out duplicates. For example, is this one example of that is well, I'm figuring a example for a duplicate check. But for example, did this user log in today, right? And you want to check this user ID or this user name, for example. A Bloom filter lets you just check, did this element, have I seen this element before in the past, right? So a Bloom filter is great for that. Now Bloom filter is not a supported data structure in Redis, but there's a rebloom module that you can use. If you use that, instead of storing all the elements, you're just checking for the existence over here, right? Both of them will reduce your memory significantly at the cost of some error percentage, right? There are 2 talks in RedisConf 2018 right now going on. I think the next talk is deduplicating data streams with Bloom filters at 3 o'clock. I don't know which room it is. And there's another one, real-time analytics. You can probably, so both of these talks will tell you how you can use probabilistic data structures. Both of them are great from a memory optimization perspective as well. Well, finally, on the set, I think this is last on the sets. Redis strings can be used as a bitmap. A bitmap is basically you're setting individual fields. A bit is basically trying to use as a boolean. Is it 0 or 1, right? So let's say that you're trying to store access control lists, right? Does this user have permission on this page? Instead of doing it in set, you can store them in a string and set individual fields of that string. Redis strings, you can do logical operations and or. So this is a great way to store data in just one single bit, right? Now, there is a caveat to this. Bitmaps are efficient if you know that there's a 40 to 60% probability of the element being present. So what does that mean, right? Let's say that you're trying to maintain a set of who are the users that logged in today, right? Now, if you expect only 10% of your total user base to log in on a given day, right? A bitmap would be inefficient because you could just store the 10% IDs in a set, it would be efficient there, right? Vice versa, if you expect 90% of your users to log in, it is easier for you to say the 10% that did not log in and have a set which says 10% did not log in today, right? But if your range of your set, is in the 40 to 60% probability chance, then a bitmap makes more sense because then it is bounded no matter how many number of elements are there. Size of the bitmap is fixed. So yeah, bitmaps is a great way to implement a set. It's just a Redis string. Use the set bit, get bit commands on a Redis string, and you can implement bitmaps. Right. So that's the section on optimizing set. The fourth section is more about lists. There isn't much you can do about lists except enabling compression. So Redis by default does not enable compression. There is a setting though which is list compress depth. By default the value of this is 0. If you are using lists, a little interlude, right? The way Redis stores lists is that it stores smaller zip lists and then it has linked lists, right? So there's a small list and then this is connected to another list as a link. It's like a train, right? Each train connected individually. What list compress depth does is the nodes in between, not at the start, not at the head, not at the tail, but everything in between, Redis can compress that. So Redis by default will not compress the nodes at the start and at the end because it expects you to insert delete elements. But if you set list compress depth to 1, it will compress all the nodes in between, right? And it is smart enough that once you start accessing the elements in the between, it will uncompress it, get you the value, and compress it and save it back again. So it is not enabled by default if you have got large lists, especially if you've got large lists with large objects and textual objects in them. Great setting to go and it's just a simple flag. You don't have to compress anything in your application code. Just go to redis.conf, change that value. You should see a lot of savings. The one thing to remember though, that this only works in Redis 3.2 and above. Quick list was implemented in 3.2. So if you are using an older version, please upgrade. The older versions were very, very memory inefficient. The older versions of lists in Redis use a linked list for each node. That was horribly inefficient. So if any of you are on versions 3.2 below, please upgrade. Right. Those are the only two things you can do for Redis list because I think internally Redis is fairly smart about how it is handling lists now, right? 3.2 and above. Yeah.
Let's say without interchaining and upgrade to 3.2, are there any improvements?
Yeah. 3.2 has several improvements actually. 3.2 above has significant improvements in Redis lists, and the man sitting behind you, Oren, actually made several improvements to Redis strings and SDS. So Redis strings also save a lot of memory in 3.2 and above. So you should definitely upgrade. Sorry. The next section is about a little more advanced, but Redis is a data structure server, right? So it has some inbuilt data structures, but it also has the primitives that you can build your own data structures on top of it, right? So the next section is how can you build your own data structures using some of the Redis Redis commands. So the first one is a Bitfield command, right? Now, this is an image I've took from last year's Reddit talk on how they built r/place, right? Are you familiar with C structures, right? A C structure, you could define, you could pretty much define, I want 4 bytes for an integer, followed by another 4 bytes for an integer, followed by 8 bytes for a long, followed by 10 bytes for a string, right? And it would then allocate this structure as one contiguous block, and you could keep repeating this as many times. You could make an array of structures, right? And the Bitfield command is essentially lets you do that, right? You can address, and as part of a much, much larger string, you can say, I want to go to position number 10 and read the next 4 bytes as an integer and get me the value of that. That's what the Bitfield command does, right? You can index into a much larger string and say, go to that position, read the next 4 bytes as an unsigned integer, or read the next 4 bytes as a float, right? So what this is from a talk from Reddit last year. What they did was they wanted to store a canvas, right? A large canvas in which you had pixels, and they wanted to store the value of 1 pixel. So what they did was you had, at each, and their pixels were only 4 colors, right? So they had 4 bits. So what they did was they took 4 bits, stored it at one position, and then they used arithmetic to say position 0 is equal to this index, position offset, you offset into that larger string. So now, if you do this, if you wouldn't have the Bitfield command, you would have essentially stored it into a list, or you'd have stored it into hash with an offset, right? That would be horribly inefficient. So the trick is, if you are trying to store an array or a matrix, a Bitfield command is awesome. It's terrific. So especially if you're storing a lot of numbers, floats, arrays, matrix, or a matrix, right? The Bitfield command is great. You will save a lot of memory, right? At the end of the day, a Bitfield command is just one giant string, and then you are indexing portions of that giant string using the Bitfield command. The talk from Reddit, it is there on YouTube. They have a blog post on that. Read it. It's great to understand how the Bitfield commands works. The documentation of Bitfield is also very excellent. But the summary of what I wanted to communicate is repetitive data structure, repetitive objects, use the Bitfield command. There's nothing stopping you from making your own data structures, right? Now let's say that you've got a complex object, right? You can use the get range, set range, get bit, set bit, Bitfield. These are 5 commands, right? That let you index into a memory structure and get portions of that object, right? There are multiple ways to write your own commands. You can write a Lua script to manipulate that object. You can write a module. This is the basis of a lot of modules that people have written. Like people have written graph modules. So if your data structure is something unique, something different, and does not fit into what the primitive data structures Redis has, it is straightforward to write your own data structure on top of Redis. Redis will then take care of everything from memory allocation to writing it into the RDB file, taking backups. So it is possible for you to introduce your own data structures and your own commands either using module, or if you don't want to go that heavy-handed, you can write a Lua script to emulate your own data structure as well. So that's the next thing, right? The 6th part is how do you optimize streams, right? Streams were introduced very recently, last year, but it is in the 4.0.x version, right? There's only one recommendation on streams. How many of you have encountered streams before or used streams? Not many, right? So a stream is like an infinite list. You keep appending objects to that list, and each object can have it's like a hash. So each object that you append to a stream is a hash in itself, right? In the sense that you can put key value pairs. So the top number is always a identifier. There's always an identifier to every element into a stream. The identifier is the Unix timestamp followed by a sequence number, right? So for brevity, I've just put that as 123.0. But at 123, what you see up there would actually be the Unix timestamp. The .0 would be a incrementing sequence number. So if you've got 3 entries into that same that have been added at the same instant, you will have that sequence number incrementing. Okay, so what is the idea, right? The point is that Redis streams as an optimization that as long as you use the same fields, it doesn't store the field names. So record number 1 has 3 fields, which is server, CPU, memory. It stores that at the first record. The next record, it says that, well, I'm seeing the same fields as my primary record or as my reference record. So it says same fields equal to true. So it just takes 1 bit, puts in a flag and says, well, I'm seeing the same fields. I don't need to save the field's name again. Yeah.
So would it save space to just put a blank, say memory nil?
You would have to put in something, yeah. Yeah.
So even specifying memory nil would be overall save the space.
Because you're not storing the field names, right? And the third, yeah. So that's the idea, right? When you go to over there, the 4th record, there it is going to use more memory, right? So yeah, the idea is to try not to avoid or skip field names, right? These are some of the more advanced configurations. So max memory samples, right? Now Redis expiry, right? If you've used expiry, you may have realized that Redis does not expire keys immediately the moment they expire. It's not flushing it from the memory, right? It is still memory. So what you can do is if you have lots of keys with very short expiry timestamps, a thing that you can do is increase this max memory samples. This is a setting in RedisConf. I think the default value is 5. If you increase that value, Redis will spend some more CPU cycles to actively delete keys from memory. Yeah.
Sorry, how short are we talking? Seconds, minutes, hours?
It depends on how many keys you have and how, right? But I'm saying if it's like 10 minutes and you've got millions of such keys, Redis is going to spend a lot more time trying to just delete the keys. So then it's a compromise that how much CPU. So the setting that we have, max memory samples, is a way for you to tell Redis how much CPU you are willing to spend to delete the keys. So it is essentially a trade-off between memory and CPU.
But you're saying 10 minutes.
Well, I wouldn't say 10 minutes. Yeah.
And I know that when you say hold it for an hour, it's not exactly an hour.
It's not an exactly. It also depends on how many keys you have. If you've got a few keys, it doesn't matter. If you got, so it's a ratio. I mean, I would say it depends on how many keys you have and how many short-lived keys you have. The more you have, the more. Yeah. Yeah. Now, a quick way to find out whether you're hitting into this problem. A simple way is to spin up a slave and look at the number of keys that the slave has versus the number of keys that the master has. Now, expired keys are not transferred to the slave. So that will give you a kind of ballpark number that there are so many keys which have expired and are still there in my master. And then that would be a hint for you to increase the value. Right? Yeah, so that's on the max memory samples. This is a new setting that's been introduced in Redis 4.0, again by the man sitting behind over there. So active defragmentation, Redis has a defragmentation, right? Every time you allocate a memory, it takes some memory from the operating system, but it does not release it back to the operating system. That's defragmentation, right? The internal allocation library that we use has, it sort of tracks this active defragmentation flag. If we enable it, it can actively try to defragment that and reclaim memory, and so that's a setting. If your fragmentation ratios are very high, try that out. There are some caveats to that. If you are using Redis modules, be wary of that. It is not enabled by default because not a lot of people have used it outside of Redis labs, I believe. But it is something that you can try out for your use case. this has become less of a problem now, but if your data is less than 3 GB, you can switch to a 32-bit version of Redis. It will save you memory because a pointer in 32-bit is 4 bytes. In 64 bits, it's 8 bytes, right? So the size of a pointer reduces. You can store less memory, but then it becomes, so if your overall data set is less than 3 GB or so, I would say use a 32-bit version. You can try it out using a 32-bit version, right? And then I think this is the last one I have. Lua scripts. If you don't parameterize your Lua scripts, Redis does not flush a Lua script. It always caches the Lua script in memory, right? Now, the right way to write a Lua script is to parameterize it with keys and args, right? Now, if you don't, and your scripts are dynamically generated, and every time you're giving Redis a script and say, we'll compile it and run it, it will keep caching all the scripts. So watch the memory usage that you're doing. There is a command which says flush the cache of your Lua script. But the right solution is to parameterize your Lua script. And finally, if you use this tool that we have, rdbtools.com, you can sort of take the guesswork out of your memory. It will sort of give you, analysis. That's the end of my talk. I'm open to questions. Quick thing, we have a cheat sheet of all the recommendations that we have. You can grab it from Ankur sitting behind there. This has all the recommendations, kind of a summary of whatever we spoke today. That's it from me on my slides. Happy to take questions. Yeah? Just 1 second, I think someone's been...
So I saw that you had the max memory samples, and I think that actually just makes the evicting of expired keys more accurate, things like that. And we actually found that we had a bunch of keys that were expired after 2 hours, but we were adding like 10,000 a second, and we had to increase the hertz value to actually get them to be evicted because we started running out of memory. And it was like way more than we had anticipated. And when we increased the hertz, it fixed that issue.
Yeah, so both max memory samples will tell you, is an instruction on how many keys it should sample in every cycle, and increasing the hertz is also helping in that. So both of them together will help you. Yeah, you're right. Any other questions from the audience? Yeah.
Hi. The first example you gave, user versus articles.
Yes.
You said let's normalize it so that we can have separately, but that also increases the number of ops on Redis?
Yes, so there are two ways you can do that, right? You can either use the pipelining and get both the keys or both the objects together in one command, in one network hop. So it's not increasing the network hop. If you know the exact keys and you use pipelining, you will get the data back together in one go. If you need a little more complexity, you can write a small Lua script which gets you both the objects together. So while it is saved separately in RAM or in Redis as separate keys, when you're fetching it, it doesn't mean that you need two separate network hops. You can get them together in the same network hop using pipelining.
Right, but for you to get the article ID, you need to get the user first, right?
Right. So that's what I'm saying. So if you want to do that, what you could do is you can write a small Lua script which says, given the article ID, the Lua script will figure out what is the article objects, and then send that data together in one batch. Right?
Thank you.
Yeah.
Is there a threshold from where we can, instead of using JSON, we go to the message pack?
Is there a threshold? It depends, right? How many objects you're saving? What is the size of each individual object? There isn't, right? I mean, if you're talking about only 512 MB RAM, you could afford JSON. It depends, right? How pressing is your problem?
So it's a huge JSON. It's just one object.
Okay.
But there are multiple reads to it. It's like hundreds and thousands of reads on it.
Right, and if it is a huge JSON, then I would say, do you need that huge JSON in every request? Do you need the complete JSON in every time?
Yeah, it's a process JSON. So we are trying to eliminate the overhead by storing the JSON, process JSON.
Right. No, I understand that. But if you don't need the entire JSON always, you can split that into separate keys. Because see, other than memory optimization, you should also be worried about network. So if you have got a big object and you're transporting it every time from Redis to your application, there is a lot of network utilization as well. So split it into smaller keys, or try to find out if you can use message pack and just fetch portions of your key into your application. I think there's a question over here. Are we out of time? Okay. I can speak separately. Thanks, guys.